because everybody will have taken it by the time school is over with today. So I'll open it up. I'll send out a remind and let everybody know that it's open, and then you'll be able to look at it. If you had any questions, then see me tomorrow morning, see me Thursday morning. We wouldn't spend any class time, obviously, tomorrow. We're going to have that quiz. All right. She's talking about the previous quiz. If you guys want to look and see what you may have missed on that, we'll open that up tonight. All right, so today we're assessed slope fields. People usually love this. It's something they really get excited about. So hopefully you're super excited. It says a slope field is a graphical representation of the slope of a function at various points in the plane. Each curve formed by the slope field is a possible solution of the differential equation. The solution curve is a curve that passes through, so on and so forth. The slope field is constructed by finding the slope of a curve at any point. We can read all those bullets. It's not going to make a lot of sense until you see them and until we do them. So just hop on down to number 1. I'm not going to elaborate too much on that. It should all reveal itself as we work through these set of notes. What I want you to do, though, is graph the following equations on the same coordinate plane that I have on that paper. So e to the x, e to the 0. So if we go here to 0, we know e to the 0 is going to be a 1. And then we should know the general shape of e to the x would look like this. It levels out towards the x-axis. It never hits a value of 0. So that's our regular old e to the x graph. Let me label that actually. So this is e to the x. If I ask you to graph e to the x plus a 1, and then it's a vertical shift of up 1. So now our graph's going to look like this. This guy then should level off towards the y value of 1, like so. That's e to the x, shifted up 1 unit. I'm going to try this fancy silver color. If I do e to the x plus 2, it takes the original graph, shifts it up 2 units. So it's going to look like this. So e to the x plus a 2. I don't like that one. And then the last one, e to the x minus a 3. Now, do it from the negative 1. So we're going to go down 1, 2, 3. So that should go through a negative 2, levels off towards a negative 3. This should be e to the x minus 3. So they're all the same graph. We're just shifting up and down. The reason I have you do that, and you have your graph, I'm going to make this a little smaller so you can keep this in view. Because underneath where you see those words, I tell you, these could all be solutions. Remember how we solved differential equations yesterday, trying to find the original function with RC? These could all be the solution to this differential equation. Because if I told you to solve the differential equation, f prime of x equals e to the x, like we did yesterday, we would have put the little indefinite integral in front of it. On the left, we would have said f prime becomes regular old f of x. The antiderivative of e to the x is itself, and then we know that we've got to do this plus c. So until we know what this c is, every single one of these guys is a solution. Here our c would have been a 2. Here's our c is a 1. Here we have a c of 0. Here we would have had a c of a negative 3. All of those could be solutions to this differential equation. That's what we had done before yesterday. That generic c is just out there. It could be any constant. All 4 of those graphs could be our solution. Keep in mind too, aren't there really an infinite number of solutions? Couldn't we also have the one that goes through here and then here? They don't have to be integers either, right? We could go through some decimals. So there are an infinite number of solutions to that differential equation, and we don't know which one we're dealing with until we are now told what point we would go through or have some more information. So if I then tell you, find the solution if we go through this point, that's what we then did yesterday. Let y be a 1, let our x be a 0. Anything to the 0 is going to be a 1. So notice how our c is a 0 here. We would then say the function that goes through that point would have been just the regular old e to the x curve because the c ended up being a 0. If we go back to the graph, give you a second to make sure everybody gets that down. If we go back to the graph, all of these infinite number of graphs that we would have on our paper, once I know I go through this point, we better be looking at the e to the x graph. So if I actually go up here to the point 0, 1, isn't that the graph that actually gave us this e to the x curve, just like the differential equation would have solved to be? Okay, so what slope fields really get at is this idea of the c and understanding there are an infinite number of solutions, and unless we have other information, all of those curves are possible solutions to our differential equation, okay? So let's dive into one of these now. So it says construct a slope field for the following functions. So here's our derivatives. We're going to write the slope field for them. Then you're going to check your solution by solving the differential equation, just like we would have done up here and like what we did yesterday to solve the differential equation. And then you're going to compare it to your graph. All right. And you see, we're going to get a little crazy, and we're going to do number 3 first. So jump to number 3, because it's the simplest and easiest. And if you look at the bottom of that paper, you're going to see some really cool stuff. That's what a slope field looks like. So that's what we're basically constructing for the problem that we are now given, okay? So what we're going to do, what we have to understand, which we've known since the first week, when we see this notation, when we see that this is dy dx, that's our derivative, we've always said this whole time that really just means that our slope is equal to twice the x coordinate. Dy dx is nothing more than your slope. So let's say I go to the point, let's go 0, 0. So take the point 0, 0. If I ask you what is the slope of our curve at that point, isn't our slope always 2 multiplied by the x coordinate of our point? So for this problem here, isn't our x coordinate now a 0? Think about then, what kind of a line has a slope of 0? So look at the bottom of the paper also. Look at all those little line segments. See all the little line segments in our slope field? What those line segments are, that's graphing the slope of those line segments. So what kind of a line segment would ultimately have a slope of 0? Right, the horizontal line segment, correct? Flat. So what we're going to do is at this point right here, 0, 0, we're going to draw in a little horizontal line segment, because that's the type of a line that has a slope of 0. Let's say I move over, let's actually go up. Let's go to 0, 1. So I'm going to go up to this point here. The slope there is also twice the x coordinate. Isn't our x coordinate there also going to be a 0? So we're also going to draw in a horizontal line through there. Now, if you look at the bottom of the paper, there's a lot of line segments, so we want to recognize some shortcuts to make this somewhat quick. Wouldn't anywhere up and down the y-axis have an x-coordinate of 0, which means all of them are going to have slopes of 0. So we can then very quickly draw in slopes of 0 everywhere, at least horizontal line segments that have slopes of 0 everywhere. Next one I'm going to do, let's say I go over here to this point, 1, 1. And I'm going to now take that point, 1, 1. I'm going to talk about how our slope is always twice the x coordinate. The x coordinate at that point is a 1. So the slope at this point, 1, 1, would have to be a 2. We're not going to measure 2 exactly. There's no way to precisely do that. What we want to do is just draw in a line with a positive slope. And then we'll start talking about how these get graded. You do have to do this tomorrow. This is always on the AP test. Very, very common thing for you need to do. So one of the ways you're going to get graded now, let's say I go to this point right here, 1, 0, or the point above it, 1, 2. Wouldn't all of these have the same exact slope? Because they're all going to give you 2 times the x coordinate of 1. So one of the things you would get graded on, if this is what you think your slope of 2 is, this is my first time drawing them on a computer, so hopefully this turns out reasonably well. Then the point above it and below it better be 2, and then all the way up and down, the x values of 1, I should get the same slope. I'm much better at drawing these on the board than I am on a computer as I look at these, so just do your best. The other thing you're going to get graded on, let's move on over here to the point 2, 1. So now let's take this point 2, 1. We know our slope is always twice the x coordinate. The x coordinate at this point is 2. So the slope at that new point, 2, 1, should be a 4. So the other thing that we would look at to get this graded, if up and down here, if these are all slopes of 2, then when I go to draw on a slope of 4 up and down here, change the colors so we can kind of see what I'm talking about, wouldn't all of these have slopes of 4? So what we would now look for is this line segment here better be a little bit steeper than the blue lines where we all have slopes of 2. And then up and down this yellow line that I have drawn in, I should have largely the same degree of slope in all of my line segments up and down that yellow line, and they should all be slightly steeper than the one immediately to the left. We'll do one more. We'll kind of try to save some time. This is a little short. So now let's say we go here. Hopefully now we're all pretty bright people in here and at home. Those all have x coordinates of 3. Our slope is always 2 times the x coordinate. So now all those should be slopes of 6. So when we go to draw these in, these should now be steeper yet than the ones that were immediately to their left. All right. If you want to, we can try to do these. I guess it doesn't take a lot of time. These would all have slopes of 8, so these would be our steepest. Let me try to draw those in one more time. All right, so that's the right-hand side. So we're halfway home, right? So people usually love these. Now we have to go to the left-hand side. So if we now go to the left-hand side, this, again, we should be able to get through this fairly quickly. Think about what this point is. This is the point -1, 1, right? Our slope is always twice the x-coordinate. Our x-coordinate is going to be a -1. So now up and down this line, when our x value is always a -1, all those slopes should be a -2. So as best you can, try to draw in these so they're the same, the positive slope. This is bad. Let me try this way. I'm going to turn my computer. Try this again. All right, to the left of that, if all of our x coordinates are -2s up and down this vertical line, then all the slopes here should be a -4. So now they should be steeper in a negative direction. So I'm trying to make these all a little bit steeper than the ones to the right of them. These would be -6. At this point, I'm getting these probably a little too steep. So then these over here are going to be very steep. And then voila, there she is in all of her glory, your first slope field, okay? I'll give you a minute to do that. Let me erase all of these. I think we understand where these came from, because there was a second thing that I wanted you to do in these directions. So try to get that down. Try to get all your tick marks written. All right, the second thing that I asked you to do in your directions, so if we went back to this, it says, then check the solution by solving that differential equation and comparing it to your slope field. So what I mean by that is, remember how yesterday we would have multiplied this dx over? We're going to do that again. We're going to solve this. Once they're separated, you're going to do the antiderivative of the two sides. On the left-hand side, you have a 1 dy, so the antiderivative of 1 would have been a y. And then on the right-hand side, you would get 2x squared divided by 2, which is just x squared, and then we get our plus c. Understand now what has just happened. By simply graphing the slope at each point in our coordinate plane, look at the original function here. I don't want purple anymore. Look at our original function here, y equals x squared plus 2. If you now look at this slope field here, don't we see, it's kind of like those pictures where if you stare long enough, a nice little image reveals itself. If we look at that graph, don't we see a whole bunch of parabolas opening upwards with just some vertical shifts in it? Yeah. So those are our infinite number of solutions. You don't necessarily want to draw this in right now, but can't we get a parabola that would go sort of like through this point and follow this path? We would get another one that's down here following this path. So if I gave you that we have to go through 0, 1, and you don't necessarily need to mark yours up, just understand what I'm talking about, then I could actually now identify what parabola we are actually dealing with if we have to go through the point 0, 1. But we don't know that without me saying what I did yesterday, that like f of 0 equals 1. If I give you that, then we know which curve we're dealing with. Without this though, these here are all of the possible solution curves that we can come up with from that differential equation. Okay? All right, number 4. We're gonna go number 4 next. Number 4 is also kind of the next easiest one. In fact, it doesn't get much easier, because if we understand that dy dx equals y, all that is saying is our slope is always the y coordinate of our point. Look for patterns to make this as quick as possible, because obviously you can see here this can be a little bit tedious. But think about, here's 0, 1, 1, 1, 2, 1, 3, 1, 4, 1. So now the horizontal lines all have the same slope. So anywhere where I'm at 0, 1, 1, 1, those slopes should always be the y coordinates of 1. So across the horizontal line now here, these should all have slopes of 1. So 1. If we go to the points 0, 0, 1, 0, 2, 0, so basically the x-axis. So anywhere on the x-axis, every single one of these is going to have a slope of 0. So across the x-axis, we get all these little horizontal tick marks. Actually, let me continue to work my way up, because anywhere we're here, let me do it with the highlighter. Anywhere we're right here, aren't all of these y coordinates going to be 2? So if our slopes were 1 below it, then the slopes across this horizontal yellow line now should all be the same, but they should be a little bit steeper than the slopes below it. And then the ones above that should be steeper yet, because these are all going to be slopes of 3. And then slopes of 4. So the top one should be our steepest. Then we still have our negatives, but again, notice our patterns. Anywhere across here, your y coordinate's always going to be a -1. So our slope is always going to be -1 across that horizontal yellow line right there. So now, -1s. And then -2s. Negatives. Steeper again, -3s. And then 4s. All right, give you a minute, because then we're going to solve this. And this one you want to be careful of solving. This is one of the big ones. So let me rewrite this as dy dx equals y. So finish out all those tick marks, and we'll solve this in a second. All right. If I have you now solve that, we're going to multiply our dx over, get that on the other side, but now the y is on the wrong side, so we got to divide that y over. So we encountered one of these yesterday, so really common. Once they're separated, we can go ahead and do our antiderivative. Remember how yesterday we said dy over y is really just a 1 over a y times a dy. So this was the derivative of a natural log of the y. And then that would equal the antiderivative of 1 dx should just give us an x plus a c. All right, then you're going to use we're trying to solve for y, so let's use our e to get rid of this. These are going to cancel. Now we want to explore a little bit. I kind of jumped over it yesterday, but this is a little more common today. This absolute value doesn't just drop out, so leave that there for a second. And we'll talk about what this is. 7th period brought it up yesterday, so we talked about it yesterday with them, so I'm going to talk about it a little earlier than I normally do. So just leave that as an absolute value of y for a minute. Then we need to review some algebra so that we can understand how this gets simplified. So if you recall, if I gave you x to the 2nd times x to the 5th, do we all agree that we add exponents when you do that? So this would be x to the 2 plus a 5. So the reason we would ever be adding exponents is because we would have been multiplying like terms. In this case, it was x's. So notice how we're adding exponents here. So the way we're going to simplify this, we're going to kind of unsimplify this actually. Instead of adding the exponents, we're going to write that as a product of e's with one of them raised to the x and then one of them raised to the power of c. Okay, follow that? Then I don't remember if this, I think it was 7th period also brought this up. So now this is going to blow some people's mind here a little bit. If I have e to the x and then I ask you, remember what e is. Remember e is about 2.7-ish. So for the sake of what we're going to talk about right here, if I tell you to take 2.7 and raise it to an unknown number, what would 2.7 raised to an unknown number give us right here? What do we think? Okay, the silence is actually kind of a good thing, because if you're going to take some 2.7 and raise it to something that we don't know the value of, doesn't that give us another unknown number? So that actually is going to become just a regular old c. Remember, the constant stands for the unknown constant. What you might see in a book, and you can do this if you really want to, just so we don't think these are the same values, some people will mark this as our first unknown constant. And then when I take 2.7 and raise it to that unknown value, I get a different unknown constant. So you'll see some people label this as the second sub c. It's unnecessary. It's not something you need to do. But some people will. The big thing that people tend to mess up is this has to be a product between these. It has to be. Okay? So then there's no reason for us to leave the c. Whenever we have a constant, we would put that in front typically. So let's leave this absolute value y equals c times e to the x. And then remember, kind of when you would have dealt with absolute values, isn't the absolute value, aren't there two solutions to this? One of these could be y equals a positive c e to the x, but couldn't it also be a negative c e to the x? Could be either one of those. All right. Now, we'll get to the plus minus thing in due time. What I want you to now think of, are we looking at a bunch of exponential curves? So a couple are easy. Like if I give you 0, 1, doesn't it look like we're leveling off towards a slope of 0 here? And then this is going to start to increase pretty quickly the further right that we go. If our c is negative, so if this is a negative, wouldn't this now just give us the negative exponential curve that looks like this, and it's going to start to decrease very quickly? So by graphing again the slope, we get all the possible solutions to this differential equation right here. Okay. Okay, one more I want to do. I do want you to see number 1. So go back to number 1. We'll probably skip 2 today. Try to catch some minutes that way. Because 2 is the only one, is the first one where you now get x and a y. So this now is saying that our slope is always the product of our x coordinate and our y coordinate. That makes the x-axis and the y-axis really easy, correct? Because either on the x-axis or the y-axis, either x is 0 or y is 0. So across the x-axis and the y-axis, all of these slopes have to be a 0. So those we can do very quickly. That if I go to the point 1, 1, all we are again doing is multiplying our x and our y coordinates together. So at this point, 1 times 1 is a 1. Go above it. This point right here is the point 1, 2. So 1 times 2 is 2, so we're a little steeper. And then 1 times 3, 1 times 4 would be 4. I'm going to go down this vertical line. So at this point right here, 1, negative 1. 1 times a negative 1 is a negative 1 slope. 1 times a negative 2 is a negative 2, negative 3, and then a negative 4. We're only going to do through the 2's, so let's go to 2. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, and then 2 times 8, that's pretty darn steep. It's hard to. And if we come down here, 2 times a negative 1 is a negative 2, negative 6. I'm sorry, negative 4, negative 6, and then negative 8. Don't do 3s and 4s. These get steep really quickly, and it gets hard to do them. So let's hop on over the negative 1 and the negative 2. So a negative 1, 1. This point here, you're taking the negative 1 times a 1. That's a negative 1. Here we have a negative 1 times 2. So that's a negative 2. So a little steeper than the one below it. And a negative 3, negative 4. In the third quadrant, we have negative 1 times a negative 1. So 1, 2, 3, 4. And then if we move on over here, negative 2 times 1 would be a negative 2, negative 4, negative 6, negative 8. All right, and then finally, mercifully, negative 2, negative 1 is a positive 2. Negative 2 and 2 would be positive 4, positive 6, positive 8. All right. Now, you never have to construct an entire slope field. Usually you get 6 to 10. I'll put the dots and you have to do that. You don't have to do an entire one, but I like you to kind of see the overall pattern, and then when we can solve it, you can kind of see that reflection. Let's solve this guy now. So same thing we've been doing. Separate your variables. So the dx is going to get multiplied over. The y is going to be divided over. We do our antiderivative. We get another 1 over y. So that antiderivative is the natural log. And then x squared over 2. And then plus our constant. Now again, let's see if we understand what we just did before. This initially is our absolute value of y. We have the same thing going on here. We're adding exponents. And the reason you would ever add an exponent is we would have had two separate e's that were getting multiplied by each other. And then to condense that, you would have added the exponent, so we end up with the one term. We actually want to kind of work backwards from that. 2.7 raised to an unknown number just produces a different unknown number. So we're just going to write that as c e to the x squared over 2. And we now know that we're getting multiplied. And then we would know that y could equal a positive or a negative c, whatever we would end up with, x squared over a 2. So what I typically then, we would have done this earlier. Let's say I graph this, because our c can be anything, right? So I'm going to do this as if c is a positive 1. So if I go to my calculator and I graph that as c is a positive 1, so there's our 1. And then we said this function is e to the, a lot of fractions here, x squared over 2. And I graph that. Does this graph model all the little tick marks that we have in our graph? Doesn't it look like a parabola opening upwards if our c is a 1? So if you look at your graph, that should take shape. If I make it a negative 1, so let's say, well, let me just insert it and it'll be quicker. So if I go in here, insert a negative in front of the 1, notice how now it looks like a parabola that's going to be going downwards. Fits perfectly into all those little tick marks that we just created with our slope field. Okay? All right, hopefully that's enough for you to understand. We're going to skip 2. It's not that it's hard. It's redundant at this point, and with our time limitations, we're going to stop with those. Next thing. So here's how this will be multiple choice wise. So this I actually cut and paste. Let me pull up Cami here. If you look at these graphs, think of the x as t. So if you look, the axis is the t. So x is the t, and then you're given these 4. Hey, there I am. And what you have to do is match these up. So there's not one set way that you're going to do these all the time. So let's kind of go in the order of easiest to hardest. The easiest way, which is rare, is if we know the antiderivative, like we just did here. So what I mean, I can't squeeze that in. So that if we know the antiderivative. So what I mean by that, look at this first one here. If we were to separate those variables, so if I were to take that dt and just multiply it over, we don't really need to finish this problem off. But if we did the antiderivative of that, wouldn't that give us the sine curve? Look at your 4 graphs. One of those 4 graphs should look like a bunch of sine curves with just different shifts in them. Whichever one looks like a bunch of sine curves has to be the solution to that dy dt equals cosine of 2 or t plus a y. All right, can we see one that's clearly a bunch of sine waves? Yeah, and it should be the bottom left-hand corner, correct? Like this here should have been the whole dy dt equals the cosine of t plus a y, because we had all these sine waves in there. That's pretty rare, and you don't necessarily want to have to do the work to figure this out. So we want to have some other ways to do this. The next one that I think is easiest is probably this guy. And what this would fall underneath is just knowing the slopes in each quadrant, or just slopes overall. So it doesn't necessarily have to be a quadrant. So when I highlight this one here, the reason I'm highlighting this one, wouldn't that one always spit out a positive slope? No matter what y value I'm going to plug in, I'm going to square it. I'm going to increase that by a 1. It has to always have positive slopes. So if you look at the 3 remaining, really of all 4 of them, isn't there only one of those graphs that has positive slopes everywhere? Yeah, that has to be that answer. So that has to be the upper left-hand corner. That's the only one that has positive slopes everywhere. So this has to be the 1 plus y squared. This one falls underneath that same idea. This is really just x times y. So if we're doing x times y, shouldn't quadrant 1 have positive slopes everywhere? Quadrant 2, all of my slopes should be negative. Quadrant 3, my slope should be positive, and quadrant 4, my slope should be negative. If we're just doing the x times the y, so we're only got 2 left, right? Upper right-hand corner and the bottom right-hand corner. If we look at the bottom right-hand, it's actually the one we just did, right? Isn't that what we just did, x times y? So notice positive slopes always in the first quadrant, negative slopes in the second, positive in the third, negative in the fourth. So this one has to be the x times y one, which we're just using t times y in this case. So that leaves us with this. And then that gives us a third option that we want to look for, is look to see when is your slope equal to 0, and really in this one, look to see where your slope might be undefined. So what I mean by slope being undefined, look at this one that we haven't talked about yet. What y value would make that fraction undefined? All right, so if we did that, doesn't the y value of a -2 cause a problem in this derivative? We haven't drawn this in yet on the 3 problems that we did. But if I ask you what kind of a little line segment would you need to draw if our slope is undefined, isn't it vertical lines that have slopes that are undefined? So if we look at the y value of a -2 and the one that we haven't graphed yet, let me get my highlighter. So here's -2. Look across this horizontal line here. Doesn't it look like our graph is going vertical when we go through that highlighted yellow line right there? So that's how we could then identify that this has to be this graph here. Okay, makes some sense, hopefully. So unfortunately, there's not one distinct way that you can do it. You want to explore all of them and see which one would work for whatever you're looking at. Okay, and then the last thing. And they've only ever made BC people do this on the AP tests. Don't usually like this very much. You have to be somewhat of an artist. Let me see how I can now do on a computer, because I've never done this before. Let me do this in red. No, black. It says for each differential equation, you're going to sketch the solution curves that pass through each of these 3 points. So what this is telling you to do is go to 0, 0. So put a dot on 0, 0. I kind of did this earlier. You need to sketch the curve that would be going through that point. Let me see if I can make this even bigger here. So if you look at this point right here, to me, it's pretty clear that these two guys all line up pretty well. So we're going to definitely connect those two. Then these are sometimes, I think in physics, they are called direction fields because they're telling you the direction in which you are then taking off. So look here where this guy is pointed. You could make an argument that this gets pointed right here, but to me, notice how we got to kind of make a right-hand turn to find this one. You will not hit every single row. So what I mean by that is I'm actually not going to hit any tick marks in this row. I'm not going to hit any tick marks in this row. To me, if we think of this as a direction field, let me get my eraser. To me, this guy is probably guiding me more up to this one. So I am going to follow it up to here. What we don't want to do, so the way they're going to grade these, you don't want to be creating angles with your tick mark. You don't want to make X's. Think about where this one points. I am, again, going to probably have to skip. If we look at where this one points, I'm probably not going to be able, oops, that's not what I want, to hit this next row right here. I'm probably going to take, think about where this is pointing. It's probably pointing up to here. So I'm going to go to this one. And then from there, this takes me pretty steep in that direction. We also have the bottom half. So it's kind of like connecting the dots, really. And I would think that mine would look like this. Let's try to get two more done. I also wanted the point 0, 1. So that's just going to say, all right, well, let's go to a different point because now it might look different. This doesn't look too different. I would say that this point goes to this line, and then this line directs us up to all of these that are getting pretty steep. And then the left-hand side, I'd probably draw in something that looks like this. Now, those are all going to look the same. Normally, I like to get to at least this one, and I like you to try one of these, because shouldn't you get a sine wave looking down here? If we were to do that one, we're going to go to this one. And the only reason I'd like, normally for people to do this one, if we do all three that I've asked you to do, 0, 1, 0, 0, and 0, -1, they start looking a little bit different. Actually, that's not the one that looks really different. This is the one, sorry. Because if I do 0, 1 here, 0, 0 here, 0, -1 here, these down here look like all these parabolas tumbling downwards if I'm 0, -1. If I'm 0, +1, I look like a bunch of parabolas opening upwards. And then people usually have some trouble with what goes on at 0, 0. So try to draw in 0, 0 here. I know I'm rushing you, but we have less than 2 minutes. And to understand that one, think about what's happening throughout this area. Doesn't it look like from both above and below the x-axis that those are all leveling off and giving you slopes of 0? Yeah, so when you sketch this guy in, this actually does give you a whole bunch of slopes of 0, so they would all line up here, and that would be our third one. All right. The problem at the bottom, not that important. You'll survive without not seeing that. I think we've actually done plenty to make sure that you're squared away for tomorrow on the quiz. Okay. If you do have any questions, though, that quiz review is posted. The answers are posted. Any questions on that or anything else, check in with me at 9:30 in the morning. And if not, we'll see you tomorrow afternoon. Okay. All right. We'll see you guys. Have a good night. Yeah, go ahead.